So, a while ago we learnt that you can't count individual electrons around a circuit. If we were to draw one, it'd be crazy. So instead, Henry Coulomb came up with the idea that we would have buckets of charge, and he called them 1 coulomb. And we have our coulomb of charge here, and very similar to what you learnt in year 8, this coulomb of charge will move through the circuit around these blobs of electrons, and while they're at the cell, they'll be picking up electrical energy. So if we just give it a little blob of energy, and there we go, and this cell will provide the energy, and the coulomb of charge will move around, and it will give that energy to the bulb or the motor, and it will disperse it. So with that in mind, we now have redefined current and voltage in terms of coulombs, and we see that 1 volt is 1 coulomb of charge. No, it's not. It's 1 joule per coulomb, and 1 amp is in fact 1 coulomb flowing per second. And we've seen already that the power of a device is current times voltage from the previous lesson, and if we were to turn that into joules, current and seconds, we'll see power is joules per second is equal to current, which is coulombs per second, and voltage, which is how many joules per coulomb. And tidying that up, we can see straight away that we can cancel out the coulombs, and it's a self-consistent equation. We get joules per second, not coulomb. Right, well, what else can we do? Well, we can now introduce some other equations. What about the energy that's being delivered? Well, if we were to look at energy, we would see that energy in joules is equal to the charge, how many of the charges there are, how much they're carrying, which is measured in coulombs, and by the voltage, the amount of energy they're carrying. So how many joules per coulomb. And it works still. If we write it all out in terms of its base units, we see we get that. And so there's an extra equation. In terms of algebra, it's written as E is equal to Q times V, and it goes nicely in a little triangle, E, Q, V. We can also look at it in terms of a delivery system. We have, in essence, electrons gaining energy here, or coulombs of charge, delivering over at the bulb and going around. So I like to think of it like a conveyor belt. Here we've got my conveyor belt, and there's my charges dropping in, and the conveyor belt moves them along, and the bulb collects the charges, doop, doop, doop. And there's two things that are going to affect how much energy we end up collecting. One is how many joules per coulomb. So what's the voltage? The other one is how much flow there is, how much current, how many coulombs per second there is. And then the final one is how long has it been going for, how time. And so what we can do is we can just count the amount of electrons falling in the bucket. And grab that one. And we end up with an equation called the quit equation. Number of charges, Q, is equal to the current times the time. Let's try it out by units. Charge, measured in coulombs. Current is how many coulombs per second. And time is how many seconds. So we have coulombs divided by seconds times seconds. So they cancel out. So this is one of my favourites, called the quit equation. And again, pop it in a little triangle, Q, I, T. Typical example might be, find the total amount of charge in a circuit. Have a go at this one at the same time. I'm going to pause at the right time. If 2 amps flows for 1 minute. I'm out of practice. So have a little go. Pause the video, give it a go. Okay, so let's have a go. Is there any on the end of that? No, there isn't. So we've got 2 amps times, there was a trap. 60 seconds, we end up with 120 coulombs of charge flowing. And final equation. What about if I want to know the total amount of energy delivered to a bulb? Well, again, it's going back to this example here. Well, if we were to count how much energy was actually in the bucket, like so, all we've got to know is the voltage on top. And so what we end up with is energy is equal to current times voltage times time. And we end up with E is equal to, and it looks better to write it this way, VIT. And again, pops itself into an equation, a triangle. Energy is equal to VIT. And it obviously makes sense, because if we took V and I, well, IV is power. And power, if you remember in the previous energy module, power is energy over time. So if we substitute in IV into power, we end up with IV equals E over T. And if we were to rearrange that to make energy the subject, we end up with taking the time, we take the time over here, times both sides by time. Let's try and grab that again, not so slick. And we end up putting it over here. And we end up with energy is equal to VIT. So all of these equations are self-consistent. One links to another all the time. Have a go. Everything you need is on page 33 and 32. And there'll be some more guidance in the Google Classroom. Take care. Bye.